Dear students, now we are going to discuss about the problem on heat exchangers and a double pipe heat exchangers. It also with the LMTD method, but the problem is differently from the previously solved problem. That is a problem number one. We consider this a problem number two. Now we can move to the problem. Here a counterflow double concentric tube heat exchanger is used to cool the engine oil having a specific heat, say that is equal to 130 kilojoule per kilogram Kelvin from 160 degrees Celsius to 260 degrees Celsius with water available at 25 degrees Celsius of cooling medium. Listen, here in the sub problem, that hot fluid is, say, that is called as the uh, engine oil. You note that is a hot fluid is engine oil, and the cold fluid that is equal to water. So clearly note that what is the hot fluid and what is the cold fluid. The flow rate of cooling water from the inner tube of 0.5 diameter is 2 kilojoule per second. Here the cold fluid that can be flowed in the inside tube, but the hot fluid can be flowed in the that is called as outside tube. So that is a slightly different from the previous problems. Normally the hot fluid can flow in the inside tube and cold fluid can flow in the outside tube, but this problem, this is the reverse. Okay. While the flow rate of oil, that is a engine oil from the outer annulus diameter 0.7 2 kilogram per second. So both are same as flow rate. The value of overall heat transfer coefficient is 250 watt per meter square Kelvin. That is given. How long the heat exchanger to be meet this cooling requirement? How length is required to meet this heat transfer area? Sorry, heat exchange from what coolant engine oil from 160 to 60 and water as a 25 degree as a cooling medium. Okay. So now we move to the problem. The hot fluid, the inlet temperature that is equal to, we know that there is a hot fluid, that is inlet temperature is equal to 160 degrees Celsius. So T1 is equal to 160 degree Celsius, and cool to the temperature of 60 degrees Celsius, this is equal to 60 degrees Celsius. So T2 is equal to 60 degrees Celsius. Here the hot fluid that can flow in the outside tube. So the outside tube that is having a diameter of that is equal to 0.7 meter. Okay, now this is the hot fluid. The hot fluid that is equal. So this is the annulus fluid. Please note that this is the annulus fluid because the hot fluid is flowing in on the outside. So it's having a diameter of 0.7 meter and mass flow rate of 2 kilogram per second and specific heat of, say, that is equal to 2130 joule per kilogram Kelvin. So there is this terms related to that is called as a hot fluid, that is annulus fluid. Now we can move to the cold fluid. The cold fluid has a cooling medium that has entry temperature of, say, that is called as a 25 degrees Celsius, but we doesn't know the T2. Here that is the cold fluid, that is the pipe fluid. This annulus fluid is not, is called as a pipe fluid. So this is having a that is mass flow rate of, say, that is called as a 2 kilogram per second, but we specific it is not given. So for a fluid having a standard conditions, that is standard fluids like a water, we have a specific heat of that is 4180 joule per kilogram Kelvin. So most of you think about that the data is not given, so we neglect that. So don't go with that type of category because water is a standard fluid. So water specific heat that is to be given, that is not given in the problem. We can take it as a standard value. Okay. Here the pipe fluid is, say, water, then engine, then hot fluid is nothing but that is called as the engine oil. Okay. Now we move to the problem. In the problem, the data that is asked is what is how long must be the area required. So listen, here there is a Q which is equal to, that is a UA delta Tm. So delta Tm, the flow is nothing but the counter flow. So for counter flow, we can be written as that is a delta T1 minus delta T2 divided by delta T1 divided by delta T2. So finally, what is delta T1? So this difference is nothing but Say that is a delta T1. So delta T1 is equal to T1 minus that is a T2. So T1 is given, T2 is not given. But in the case of delta T2, you may know that is a delta T2 is equal to T2 minus T1. But we need the cap small T2, that is a cold fluid outlet temperature to find the delta T1. Before that, you may know how much length is given, that is u is equal to u, then u, that is area, that is equal to surface area when we calculate 2 pi rl into delta t lm. So here the diameter is given, so we are going to find what is the length required to for this particular heat exchanger area. Okay, now we can find the small t2 for calculating LMTT. In a previous problem, I already told any three temperatures given means we can go to the LMTT. But here in this problem, three temperature given, but fourth temperature required for calculating delta TLM. How we can find out the fourth temperature? Because here the heat gained by the heat that is lost by the hot fluid, that is heat lost by the hot fluid is, that is a heat gained by the cold fluid. So here in the diagram, what are the heat that is given by the hot fluid is absorbed by the cold fluid. So QH is equal to QC. So QH is equal to nothing but that is MH into CPH into then T1 minus T2, because cold fluid having a delta T temperature T1 and T2, which is equal to MC into CPC into that is a small T2 minus T1. So here that is equal to CPC, that is not written clearly. So for equating those two terms, I can written clearly in here. So MH into CPH into T1 minus T2 equal to MC into CPC into small T2 minus T1. So in that problem, please note that mass of hot fluid that is given. How much? Uh, sorry, mass of hot fluid that is given, so which is equal to 2 kilogram per second. Specific heat of hot fluid is given, so which is equal to 130. The temperature T1 is given, so which is equal to what, 160 degrees Celsius. Then T2 is given, the T2 is equal to 60 degrees Celsius. Here the mass of cold fluid is given, that is equal to 2 kilogram per second. So specific heat of water is given 4180. So small T2, that is the small T1 that is given is 25. So what is the remaining unknown factor in this equation, that is called as a small T2, that is a cold fluid. By equating this term, finally we can get the cold fluid temperature, which is equal to 75.88 degree Celsius. Okay, so there is a outlet temperature of the cold fluid. The T2 is equal to, so that is equal to 75.88 degrees Celsius. So you know already in the problem given T1, then capital T1, capital given, small T1 is given. You find that small T2. Then we move to the LMDT condition. Here, wait, just add one slide then. Okay. Just we move to the LMDT condition. Here, what is the LMDT? So for LMDT, delta T LM, sorry, not LMDT, delta T LM for the counterflow heat exchange is equal to delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2. Here, what is delta T1? So delta T1 is equal to, so from the diagram, delta T1 is equal to capital T1 minus small t2. So capital T1 minus small t2. Here delta T2 is equal to, here the delta T2 in the condition, which is equal to capital T2 minus small t1. So capital T2 minus small t1. Here it is a 160 degrees Celsius minus T2, that is 75.88. Then we have 60 minus 25. So 60 degrees Celsius minus 25 degree Celsius. Okay. Here we are getting that value is equal to 84.12 degrees Celsius. Here it is equal to 35 degrees Celsius. We substitute the delta T1 and delta T2 here from in the above equation. So which is equal to 84.12 minus 35 divided by ln of 84.12 divided by 35. So finally you are getting that is delta T LM is equal to 56.01 degree Celsius. So after finding a delta LMDT, you may substitute in the equation that is a Q is equal to that is UA delta T that is a LM. So delta T LM you find that is U heat transfer coefficient Q is given. U is given. What is a Q? Q already you know Q is equal to QH is equal to what? QC. So Q is equal to there is a QH is equal to MH into CPH into capital T1 minus capital T2. So mass of hot fluid 2 given into 2130 joule per kilogram Kelvin into 160 minus say 60. From that you may calculate it, then Q is equal to that is a 426 kilowatt. Better you find the value in the kilowatt, but here in that condition mass is the kilogram per second, so joule per kilogram Kelvin into that is a degree Celsius or Kelvin, both are same. Kelvin cancel, that is a joule per second we are getting, that is a watt. So for divided for the value that is divided by 1000 we are getting this is a kilowatt. So finally you can get the 426 kilowatt. So substitute 426 kilowatt in this equation here. 426 kilowatt is equal to U already given in the problem. You know that U is equal to how much? 250 watt per meter square Kelvin. So better you substitute 0.250 kilowatt divided by there is a meter square Kelvin for converting to watt and kilowatt into that is the area into there is a delta TLM which is equal to 56.01 degree Celsius. Already I told Celsius, here the Kelvin are same because so this can be written as 0.250 kilowatt per meter square degree Celsius because per degree Celsius and per degree Kelvin are same. How it is same? So 30 degrees Celsius, 31 degrees Celsius, difference of 30 degrees Celsius is equal to 1 degree Celsius. So then you may substitute the Kelvin. So 304 Kelvin minus 303 Kelvin is equal to 1 degree Kelvin. So both are equal. Per degree Kelvin or per degree Celsius is equal. But somebody you can find the value in degree Celsius plus 273. 273 you can find that is a 274 Kelvin. That is a totally wrong. So 1 degree Celsius is equal to that is 1 degree Kelvin. So better you can return degree Celsius into area into 56.01 degree Celsius. So Celsius cancel. Here it is a kilowatt cancel. Finally, you are getting area in terms of meter square. So here area you can find that area which is equal to so area. So sorry. So Q is equal to this is a way to find area. Another one method is Q is equal to delta T that is a LM. So area is equal to Q divided by U into delta T LM. So area is equal to that is equal to 2 pi RL. So which is equal to Q divided by U into delta T LM. So this is the second method you use. So this is the first method. So in the first method you might find what is the area. Area you are getting is equal to somewhat meter square. Okay. So what is this area? This area particularly usually surface area, that is a 2 pi RL, otherwise pi dl, so which is equal to somewhat meter square. So you need a L. L is equal to area divided by that is a 2 pi R. Finally, after substituting the value, you may get the length of this heat exchanger required is 19.37 meter. So this is the length of heat exchanger required for inlet temperature of 160 hot fluid temperature 162, T2 having a temperature of say that is called as a 60, and water temperature that is a T1 of 25 degrees Celsius to T2 was which is equal to 78 degrees Celsius. Okay, So this length is required for that much heat exchanger area. Okay, so please note that here you are going to equate this QH and QZ, finding the fourth temperature. After you find LMDT, then second step is you to find the area. Then area is somewhat meter square. That area is surface area. Don't take it as a cross sectional area. That is equal to 2 pi RL. So from that you know R is given. So inner diameter. If you consider cold fluid having inner diameter of say how much, the problem that is given us what 0.5 meter. You substitute the value in the 0.5 in terms of radius. You maybe get the length. That length is equal to 9.37 meters square. Okay. Thank you.